Okay, so welcome to this workshop / lecture thing on introducing neural networks with PyTorch. I understand that a lot of you already know about neural networks and machine learning. We're not going to go too in depth into sort of the inner workings of neural networks or the maths behind them. This is going to be more of a practical, hands-on learning about the ins and outs of PyTorch. So yeah, bear with us. There will be some theory, but it's going to be very, very high level. So my name is Matt. This is Surbhi, and we're part of the ICCS. And yeah, we'll just dive into it. So it's going to be a very quick lecture, probably not going to take 30 minutes, about 10, 15 minutes. And then the rest of the session is going to be a teaching, code along, try things out yourself session. We have a few people like within the ICCS around to help. But we'll have a break at about 10:30, go and get some coffee. Then there'll be another hour of teaching. And then, as you know, we'll go to lunch at Churchill College from 12 until 1:30. Okay, so at this point, I think it would, based on one of the sessions yesterday, I think it would be great if people could just navigate to this link. You can access it in one of two ways, using the full link here or the tiny URL. So this is the course material for today. Or actually, have people downloaded this already, or have people cloned this already, or yeah. So has everyone got to the material? Who hasn't got to the material? Yeah, I'll just give you a few minutes. It's all fine, okay. So this is the material for today. Once you're here, just copy the link and then just try and clone it. Can everyone see my screen? It's probably a bit small. And that's going to take some time, but well, it's going very slow. Okay. Right, okay, we'll just let that go, and if anyone's having difficulties, we'll come back, we can help you. We've got other ways of running this course, so all is not lost if you can't clone the repo and run it locally. So that's one way of doing things. We have other ways as well. Okay, so this workshop that I'm delivering is a second iteration of one that was delivered last year. So if some people are here from last year, there's not going to be too much of a difference between last year's material and this one, but they have recently, Jack and Jim have recently published a paper in the Journal of Open Source Education. So if you want to have a look at this paper after the session to understand our thought processes and how we developed the material, then please do. So today the learning objectives are to provide you with an understanding of the structure of a PyTorch model and the typical ML pipeline, introduce different functionalities that PyTorch may provide, and while we're doing that, we want to encourage as much as possible good research software engineering practices, particularly around the careful consideration of processing data for training ML models. So in terms of specific ML content, there's nothing really like particularly new here. It's ML for classification and regression using artificial neural networks, and we're going to be mostly dealing with tabular data. The material does include other examples on CNNs, and I encourage you, if you're interested in using CNNs for your work, to go through the material after today's session. It's really good. I think it'll be really helpful for getting you started, but we're not going to cover that today. I don't think there's enough time. Okay, so a quick overview of what a neural network is and some of the applications. So as many of you already know, machine learning is basically function fitting to some data. And the learning process can be supervised, unsupervised, semi-supervised. There are so many different flavors of learning, but today we're going to be mostly dealing with supervised learning. So this is a process of fitting a function to some data. We have some x points, we have some y points. We want to fit a function that maps x inputs to y values. It's very simple. We know what the functional form of this is. It's y equals mx plus c, and our the parameters that we want to fit are the gradient and the intercept. So, as I said, we're essentially fitting a model which describes some data y. So these problems can all be solved analytically. There's no we don't really need to use any special method for this, but generally speaking, these problems can also be solved using a technique called stochastic gradient descent, or some variant of it. So let's go back to a straight line. What happens if we differentiate a function? This is a very simple question, but what do we get if we differentiate a function? Anyone? Okay, I was expecting a simpler answer, but well, we get the derivative, we get the slope, we get the slope of the line, in this case, y equals mx plus c. But what's a more fundamental way of viewing a derivative? So, yeah, it's the rate of change, but it's also, ultimately gives you a vector which points in the direction of steepest descent, or sorry, ascent of a function. So if we go back to this, just y equals x, we take the derivative, dy over dx equals 1. The direction of steepest descent is pointing to the left. Okay, this is a bit of a contrived, simple example, but it kind of illustrates the basic principle of stochastic gradient descent and optimization. Okay, so in order to apply this technique to neural networks, we need some way to match our predictions to our to match the predictions to our observations, and we do this with something called a cost function, which measures the error between the function that we've learnt and our reference values y. So normally we consider this mean squared error, which has this y minus f of x squared functional form. Why do we use this? Well, it's differentiable. We need to use the squared because we sum the errors. If we don't square the errors, then all the errors cancel out. So the squared is absolutely essential, and we have to normalize, because if we didn't normalize, the error would scale with the number of data points. So the whole principle behind this is that, given some functional form, we have some parameters, and if we take the derivative of this loss function, we can nudge the parameters in a direction that minimizes the error or the loss. Right, so as this applies to a straight line fitting, you can see the differences there. We substitute the y equals mx plus c, and the principle is just basically nudging parameter m and c by some derivative multiplied by some learning rate L. Okay, so you've probably seen visualizations of this before, but I think it's quite helpful to see. You can see the loss, if we gradually step in the direction of steepest descent down the loss, the fit between the line and the data points improves. And for another example, this is just mapping mapping the size of a property to its price in dollars. If we just step down the loss function in the direction of steepest descent, we can see that the error between the the data that we have and the fit gradually decreases. So just to recap, to fit a model, we need some data, a model, a loss function, and an optimization procedure. Often this is with stochastic gradient descent, but there are other flavors. With neural networks, which we'll come on to, you often need quite a lot of data. They're very data-hungry processors. So how does what I mentioned apply to neural networks? Well, it's pretty much all the same. Neural networks tend to be a lot more complicated in terms of the number of parameters, but the whole principle is of just iteratively nudging parameters to minimize the loss using stochastic gradient descent. This process is a bit more complicated, and it relies on something called the chain rule, which I'm sure many of you know. But if you want to learn more about this, there's no shortage of resources on the matter. Just search for backpropagation, and you can really get into the weeds of how all of that works. Okay, so what does a neural network look like? First of all, they come in they have many different names. So neural nets, dense networks, multi-layer perceptrons, artificial neural networks. But the principles are largely the same. We have a series of input neurons, these circles and neurons, and these lines between the neurons are basically the weights. So we have a weight matrix usually multiplied by some activation, the activations that we return between each layer, plus some bias vector. And the whole principle behind neural networks is the application of this nonlinear activation function. Without this, it's basically just a series of affine transformations. So one layer is pretty much equivalent to as many layers as you subsequently apply. It's just the multiplication of matrices plus some constants. So the activation function is absolutely key here. And there's some justification for using activation functions from biology. There's some people seem to suggest that they mimic the function of neurons in the brain, but I'm a bit skeptical of that myself. But anyway. So if you want to learn more about activation functions, do click on the PyTorch documentation. There's a lot of information there. Okay, so normally neural networks are used for one of two things: classification, so assigning a semantic label to something, is it a dog or a cat, putting something into a specific bucket. Regression is estimating a continuous quantity, mass or volume, or the continuous values of gradient or the intercept, as we showed in the previous example of straight line fitting. Right, so we're going to be exclusively using PyTorch today. There are other deep learning frameworks like TensorFlow. I think PyTorch is by far the most popular as of today. TensorFlow has fallen out of favor a bit. It's perhaps used for more production code, and it's being superseded by JAX. I've never met anyone who's actually trained models in C++ directly. You can use PyTorch's TorchScript API if you want to import your PyTorch models into your C++ code. There's another talk going on simultaneously with this, which describes how you can couple your PyTorch models to Fortran as well. So people are doing this. It's very important, particularly in climate sciences. So who hasn't used PyTorch before? Okay, so quite a lot of people. I encourage you today, and we're going to try to demonstrate this, but just using the documentation as much as you can, and I'll show you some nice tricks as well that you can use within the terminal to help your development practices. So ChatGPT is great. Okay, so I think has everyone got the material and cloned it? Is that all gone through okay? Who hasn't got the material? Is there an issue with downloading it, or? Oh, is it just? Oh, really? Has anyone else experienced difficulties getting the material, or are we all okay? Okay, I'll just move on. So if all else fails, we do have people can just use Colab. So I can distribute this link later if people are having serious difficulties. But what I want people to do is to try to deploy the code locally. So we have a slide on this. You can do one of two things. You can install it inside a virtual environment. As so, you can use Conda if you're more familiar with Conda. You can do whatever. You can use Jupyter notebooks. I mean, you have to use a Jupyter notebook in some form. You can either use VS, if you want to use VS Code, you can. Use whatever's comfortable for you. So can people just have a quick go at deploying material?
Could people raise hands if you're able to go through the link?
I'm going to show how it's done if that helps. But okay, so yeah, I can just go back.
Once you clone, you're supposed to create a virtual environment.
There's a slight error with the slide here. So obviously, you cd into the directory and then you pip install dot. Regardless of whether you use a virtual environment or a Conda environment, the step is the same: pip install. Yeah,
Yes,
so
within the repo.
cd into the directory and then pip install. Yeah. Yeah. So if people don't want to use GitHub or clone it or install it locally, you haven't got enough space on your computer, just follow this link onto Colab, and all the materials there as well.
So if you want, you can just bypass all of the GitHub space and directly open the stuff on Colab if you want to.
We're having the same problem as yesterday. But the internet's so slow.
Are you guys able to open the exercise? Could you please raise hands so that we know?
Yeah, I'm getting it as well. Yeah. there's a few more times, shouldn't there? Yeah. It's mine taking.
I will just repeat that if you're not using GitHub, you can access the exercise through Colab. It's a pretty straightforward process.
Excuse me? Yeah, yeah.
Just go to the URL.
So if people are having serious difficulties getting the material, I think you can change the network that you're on. So instead of using EduRoam, you can use UniofCam Get. Try that. It's got a lot of dependencies. Like Torch is massive. Yeah. We can all just go upstairs and Okay, I'm conscious of the time, so is everyone happy for me just to move on for now, and then we can come back to these issues later? Okay. There were lots of other resources. I just wanted to note that if you want to learn more, there's this course by the University of Amsterdam called UVALD DLC. Yeah, they have like PyTorch tutorials on absolutely everything. So graph neural networks, yeah, using JAX, energy or autoencoders. Yeah, I've used these a lot. I think they're great. There are videos as well that you can follow. So if you feel that you want to learn more about machine learning, deep learning, this is a great resource. If you wanted to look at that tutorial. Yes, they don't. Thank you for finding. Yeah, that is. We were expecting people to realise that. Yeah, that is something that we'll amend it after the session. But for now, yeah, sorry about that. And also, Blue One Brown. If you haven't heard of him, he's great for visualizing linear algebra, machine learning. Go through that course; it's absolutely amazing. I've learned more from that than all of my sort of undergraduate courses on linear algebra and machine learning. So. Okay, so exercises. Once you all get to this point, we have two exercises. The classification example. So the whole idea is to train a neural network to classify the species of a penguin. There's this really great data set, which is really fun to use, which basically has physical features of penguins as well as other features, and you have to decide which features are best for classification task. There's also regression. We'll remove mass from the data set, and the idea is to then predict the mass using other physical features. So we might not get onto that today, but I just wanted to mention it just in case we do. Okay, I'll just go to material. So you either have access to the Colab at this point, or you've deployed it locally. Mine's still taking an age to deploy. Fortunately, I'll do the Blue Peter thing of going back to the one that I made earlier. I'm just going to cancel it because I've already got this installed. Okay, so Are we all okay? Is there anyone still struggling to get the material or access Colab? Let me know if you are having issues. I can help. Okay, so sorry about that. So we have this Penguins data set. The first task is just to look at the data. So I'll just show you how to do this first, and then you can have a go yourselves.
I hope everyone is clear about what we are trying to classify here. Do you guys know? Okay, so we are going to classify penguins on the basis of the species that they belong to, using certain physical features that we have, some information on the islands that they're usually found on, and the year of collection of the data. So this is how we load the data. This is a data set that is available online, and you can simply load the data set using an import function here.
Yeah, so as Surbhi says, we have some rows of data. We have columns of features, so species, island, as well as its bill length, bill depth, flipper length, body mass, its sex, and year. So the first task is, what do people think we should use in our classification task? What do we think will help us to predict the species of a penguin? Obviously, we can't use species here. We're going to drop that. Sorry? All the rest. Okay. Do you think there's a problem there? Yeah. Do you think any of the features will introduce bias? So do you think we should use island? Yeah, I'm kind of steering you that way. It's not unreasonable, no. I mean, and of course we can try it as well. Like, I mean, I would probably say yes, it's very likely to be predictive, but it could be a source of, it could be a source of bias. There might be some penguins that have moved island due to some sort of environmental reasons. Yeah, we could have moved them for some reason as well, for protection reasons. I don't know. I'm just speculating as to why that might not be ideal. What about year?
So feature selection basically is a very intuitive process. You can use your domain expert in this to sort of understand which features might be useful. You can also use something called correlation matrix. So correlation matrix basically tells you the correlation based on the numerical values of the features. So those features that are highly correlated may be just numerically correlated, but may not be physically relevant, so that's a slippery slope, but you can still try. There are few algorithms that are available online. Some are suggested by scikit-learn that can help you select your features, but it's always it always just depends on the problem that you have and the dimensions of your data set. So here we are just going by our intuition, and the safest option here would be to just go with some of the physical features of penguins, because that would obviously be like a good indication of what species the penguins belong to. But we are also including, are we using anything else?
Yeah, there's another one. But just to follow up on, yeah, I would say the same is true for that feature. It's going to introduce bias because due to certain environmental changes, certain species might have moved to a different island. Yeah.
They're on the same footing, are they, like in terms of picture selecting categories and numeric at the same, are there any ways of there, or is that?
We can, but I think the question is, can you use these kind of categorical data in your prediction, or? Yeah.
Is there anything to worry about if I'm aside of
I mean, off the top of my head, I don't think there is anything specific to worry about there. It can be very informative, so I wouldn't just.
So all you have to do is just encode your data to numerical values and use it there. But they can absolutely be like very informative.
Yeah. Okay. So yeah, also going back to Ireland, there could be some species of penguin that are massively represented there. I don't want to be picking on you, but there's some, that are massively represented there, whereas others are higher in number and on different islands. So that's why we should probably reject that. So I'm just going to note down some other features, some of the features that I think we should use. So we're probably going to use the physical features like build length. We'll use build depth. So use flip length, body mass, as well as, do you think we should use sex? Yeah, exactly, yeah. Say that again, sorry. The context in what respect? Yeah. Yeah, exactly. I think the point of this exercise is to produce something, produce a general classifier. Of course, if you want to overfit your model to be able to predict something on a particular island, then go ahead. But the point of this exercise is to, yeah. No, it's a really good question. Yeah. Okay. So you haven't.
I didn't really.
Yeah, I don't. Well, I guess the whole approach here is just to choose physically meaningful features to predict the species of a penguin. Yeah, that's the approach that we're taking here. But yeah. Yeah. Yes. Sorry, shall we talk about it? No, it's fine. Shall we talk about it? We can have a chat in the break. Sorry. But also I'm conscious of the time. We are going a bit slow. Okay. So what we're going to do now is just create a torch data set. We're basically packaging the data set up in a way that PyTorch will understand it, and we can create a model. So we've created this for you already. This is, don't get too confused about this. This is all to make the next set of tasks easier. But the whole point is to inherit from Torch's dataset class and then just build on top of that. So the Torch dataset class is an abstract class. It requires you to implement both the length and the get item. So the length corresponding to the number of examples and the get item function, which allows you to just select using square brackets on that data. Is everyone with me? So we basically have to implement these so-called double under or magic methods. Does anyone know what I mean by that? Or is this the first time they've ever encountered magic methods? I'll just illustrate this very quickly. But yeah, you have, say I have a list of numbers. If I want to get the length of that, I just for length. And under the hood, what's actually happening is we're calling this method length. And the same for get item. If I want to get the zero item under the hood, that's actually just get item. Oh yeah, I need to provide a param. Okay. So this is what the class looks like. To instantiate it, we need to provide 3 arguments. The input keys, so the features that we're going to select, so the physically meaningful ones, the target keys, that's going to be the species, and then it does some processing on that. So it loads of data, it does some sort of data wrangling with pandas, and then we implement a length, as I just described, which just gets it from this function split. It's not important to understand every detail of this. It's quite, quite tight, very well written Python, but the exercise, well, let's just have a go at just instantiating that. So first of all, this is probably not very good code because I'm just copying, or I'm just putting the list into the input keys directly. So maybe features equals real length. What else did I miss?
Just to remind everyone, in this step, we are just converting our original dataset to a PyTorch compatible format. which we usually do not do when we're using any predefined models from scikit-learn. But PyTorch requires the dataset to be in a certain format, and this is what we're doing.
Okay, so if you run through that task, you get a series of tuples. These are our input features as the species. That all makes sense? Yeah. Okay, am I okay to move on? Is anyone still typing?
We can repeat if you guys want to. It's really important that you guys understand what we're doing.
And don't get too worried, we do have solutions to these tasks, so you can have a look at them after today. Okay, so the question is, can we use what we've got from our class and just feed it directly into our PyTorch model and then train it? The short answer is no. You can't just pass these tuples of numbers or strings to a neural network. We need to express them as torch.tensors. And torch.tensors are basically the fundamental data abstraction that's used by PyTorch. You can see them as equivalent of NumPy ND arrays. There's a lot of complexity going on under the hood, but yeah, so the whole idea is to build a computational graph, which we'll go into a bit later. So we need to convert them all into tensors. We also need to convert our species, which is a string, into something that PyTorch can understand. So what we're going to do is use something called one-hot vectors. So we'll use basically a unit vector where the maximum value corresponds to the first class. Again, for the second element is the second class, and the third element is the third class. So these kind of orthogonal unit vectors correspond to our classes. You might be asking, well, why can't we just use numbers for this? Why can't we just use ordinal values? Well, if you use a series of numbers, that kind of suggests that some classes are closer to each other than others. So if you have 1, 2, and 3, 1 is closer to 2 than 1 is to 3. That makes sense. Okay. So the next step is to actually implement this into code, and we have this Penguin dataset. And what the task is to, well, there's some description here about what you should do, but the whole idea is to add 2 lines of code here. So task 4, exercise 1, convert the features to PyTorch tensors and convert the target to a one-hot vector. So if I give everyone a few minutes to have a go at that, if anyone's really struggling, I'm kind of happy to talk through this. Well, I'll be talking through the solution later anyway, so if you just want to relax and enjoy the show, you can. But it might be quite useful just to have a quick go at that. So, yeah.
Okay, so in the previous step, we just created a dataset which is PyTorch friendly. And in the next step, we are implementing a few transforms to the dataset. So a lot of times when you get the data, it is not in a very good shape. Sometimes you have outliers, sometimes you have garbage values. And it is machine learning. So the data that you're feeding is one of the foundations, and you should make sure that the data is clean enough and in a good position. So whatever transforms that you want to apply to your data set, it is going to be there after you define your PyTorch data set. And also PyTorch works only with tensors. So in the transformation step, we are going to convert the data set in the form of tensors.
Yeah. Oh, yeah.
Anyone, any questions? You can ask questions. Or are you guys lost already? So
That's already been dealt with, so don't worry.
So today in this exercise, we are not.
Yeah. So when we iterate over here, there shouldn't be any missing values as far as I'm aware. I could well be wrong. So please check. But that, I think in the class that's been written, that's already been dealt with. So yeah. Yeah, so we've got this function here, which, yeah. Any other questions? Yeah. Okay. All right.
When is it fighting?
Can you install the have you installed the virtual environment?
I think so. I think I'm in the version. I can even come back and do that.
I'll pick up the virtual environment and do it. Okay, so the first task is to convert the features to PyTorch tensors. So we can basically just use from import tensor, then tensor. That's what we're really looking to do. There's a slight complication here because when we use data frames, it automatically loads the data as floating point, 64-bit floating point, which we don't really need to do. We should probably consider converting that into 32-bit floating point. It's very rare and very unusual to use 64-bit precision when training neural networks. So, okay, what we're doing, this equals tensor beats. And I need to do some imports. I can't put a number on it, but particularly when you start to use GPUs, hardware that's specifically designed for neural network training, there's no real good reason to use floating points, a 64-bit floating point instruction precision. Or the hardware's been specifically designed with these kind of tensor processing units in mind. So, and it will leverage that a lot faster. There'll be a lot more sort of, compute. Yeah, I suppose that makes sense. Yeah. But it probably does, but I don't think it's really essential to I mean, I think it will perform just as well with 32-bit when you train a model. It's going to get to the same optimal point. Yeah. Yeah, I mean, there are certain models where you just don't need 32-bit precision, and it varies depending on the model. If you're running an inference when you're just making a prediction, there's no real good reason to do that at 32-bit precision. Like you can go, like there's some models, I think some certain language models now that are training it in int8, and like and also there are certain what's it called, data types that have been specifically designed for machine learning. So bfloat 16, I think, is another one. So there's basically a data type that's been if you understand floating points, which I'm going to struggle to explain now, but it kind of pushes all the things to a certain part of the representation so that you can leverage that better. Yeah. Okay. So that's the first task, which just I should say this line of code. This just basically gets an index in the data frame of index IDX, and it selects the features as requested by this input keys input variable parameter. Sorry. Okay, so the next task is to get the targets. So the way we do this is using torches. So I should say this is probably the hardest part of today. Like the data wrangling does take a bit of time in any machine learning any machine learning task. So don't be too concerned that this is a bit difficult. Once we get through this, it'll be a lot easier. So we're going to use this I function that Torch provides to get our one-hot vectors. So if you think of 3 as the number of, so species could be, let's just, for illustration, just do A, B, and C. And you know that within lists, you can just do index A to get the index where that value exists. And we can basically just use that information to get the vector. That gives us our tensor back. That all makes sense. Imagine this is a species of penguin. We've got A, B, and C, and we're getting our unit vectors back there. So in the code itself, that looks like this. Target names. One way of doing it, but sorry, I'll go back in a minute. Okay, does that all make sense? Furiously typing.
So in this step, we have just extracted the features, the input features, and the target variable. So feeds is basically the input and TGTS is the target.
So we're just creating a 3x3 identity matrix, and then we index at target names dot index targets. I think that will throw an error, but because I'm actually just putting a tuple in, I need to get the actual index of the tuple there. That's it. Yeah, exactly. Yeah. So I will make the mistakes when I type, I'm sorry. Yeah, it's not easy for me. Yeah. Any questions about that? Do you want me to make my screen a bit bigger? Has everyone got that code? I can always come back to it if you need it, but okay. Moving on, we're just going to do exactly what we did here in task 4. So create and copy this. For now. Yeah.
Feeds. That will be FEATS.
No, it's fine. I'm iterating over the data set. It'll be fine. Oh, that works. Okay.
So in the last step, we just extracted the features and the target variable. In this step, we are just going to subset the dataset into a training dataset and a validation dataset. As the names are like intuitive, training dataset, we are going to train the model. Validation, we are going to validate the performance of the model.
Oh, I know why. Yeah. It's because I'm iterating over something. Sorry about that. That's a bit confusing, but I was referring to a variable that I had previously iterated over. So yeah. So is that all okay? Okay, now you can see that we get a tensor of our features and a tensor of our species. Okay, there's another way of doing this, which I'm not going to go into. Hello? Yeah. Yeah, sorry, I forgot to explain that. Yeah, so within the Penguin dataset class, which you can have a look at, there's some logic which pulls out the training dataset, depending on what the value of that Boolean is. So we need to use a validation set because we want to separate some of the data during training. And in this particular example, we're choosing to, if you want to look at the code, we're choosing basically 10 examples from each species. So in total, there are 60 and 10 examples of each species and sex. So we have 60 examples altogether within the validation set. And we basically have this stratified split because we want to eliminate any sort of bias when we come to testing the model, because you could just choose a validation set that's proportional to the number of species in the training set, but we want to be careful not to kind of to separate out that bias within the training set when we come to validate it. I think that the way we're doing this here is a really good example of how you can structure projects. So one of the outcomes of today is that hopefully, if this all goes well, you'll have a bit of code which you can use as a basis for all of your projects going forwards. So separating out the logic into a separate class, that is good for many reasons. Object-oriented programming, you kind of separation of concerns, it's more modular. Yeah, it just becomes easier to modify and all of those things. It's very good programming practice to do that. What will happen if I put? Or you can try that if you want, but there's nothing in the class which. Are you saying that within here I've? Oh, okay. So within the validation set, we are. That is a good question, actually. I've forgotten how that logic works. Sorry? Oh, the question is, because I've included sex in the features itself, which I pass when I instantiate the Penguin dataset, I basically was just explaining how I've done a stratified split of the data, which includes 10 examples of each species and sex, so 60 examples altogether. What happens if I don't include sex in the features? I think you'll have to look into the code of how this all works. Yeah, so we're still doing the split. So the sex is still used, yeah. No, we'll still get 60. Yeah, so we're still using sex to do the stratified split within the validation set. Yeah, so regardless of whether we pass it as feature or not, we're still doing that split. Okay, so has everyone got data that looks like this? I appreciate that this is a bit complicated, but once we're past it, it should be a bit easier. Fine. Yep. Oh yeah, absolutely. Jesus. Yeah, thanks for that suggestion. I completely forgot about our workspace. I have a channel for our. There is, yeah. Well, I might deviate slightly from these solutions, so yeah, so it might be faster just to get solutions. I'm going to move on. It's probably not the greatest way of doing this. I'm just going to say, because I've hard-coded these transformations within the class. There are more general ways of doing that. If you want to apply different transformations, you can provide functions as arguments to other functions. So this is what this task 4B optional exercise is. It basically talks about how you can use the torch vision transpose compose functionality, but I'm not going to go into that today. But there is a solution of how you do that in the solutions notebook. Okay, so the next thing, yeah. To standardize your data or not to. I guess this comes through, I mean, it's going to be an iterative process. So I think for certain things like categorical data, you're going to have to convert that into a way that PyTorch will be able to interpret it. We're going to talk about normalization as well in a bit. So that's a very important part of training a neural network. You'll see that it just takes a lot longer to train without, or train very poorly without normalization. So yeah, we'll get onto that in a bit. Okay, we've got about 15 minutes until the break. So the next step, which is kind of idiomatic PyTorch, is to create a data loader, and this can be a bit confusing because we've already got basically a class that we can iterate over. We've got an iterable, which gives you sort of pairs of the features and the target, but we're going to now wrap that into a data loader, and this gives us a few sort of quite nice features, like being able to use mini batches. This is important for a number of reasons. Performance, in particular, because modern day hardware requires you to throw lots of data, particularly GPUs. Like we need to be throwing lots of data at it. So we will, as you'll see in a bit, we'll feed the data loader with a parameter called the batch size, which can have many different values. It's something that you'll have to kind of, a high parameter that you'll have to tweak when you train. I should say that the batch size probably scales with the amount of data that you have. If you want to use a too high batch size, it often overfits. So This is something that you just need to play around with. The data loader also shuffles the data during each epoch. This is really, really important because it avoids accidental patterns from emerging when you train. So if you can imagine not shuffling your data, you just have one class followed by another class. The classifier will be very good at just detecting the first class, and then it will get very good at detecting the second class, and it won't learn to generalize very well. So you need to intersperse all of your examples, and that's how you do that with shuffling the data. And also when you're constrained by memory, often data sets don't fit into memory, particularly, well, all the large language models that are being used today, vision data sets. You can actually read these in parallel using, which I'll show you in a minute. But for this task, it doesn't really matter, but I just wanted to mention that this is something to consider if you've got very large data sets. Okay, so the next step is to create a data loader. You can just have a few minutes just to play around with that yourself. This is what the data loader looks like. Like that, it takes a batch size, whether or not to shuffle. What else? Number of workers, I think. So I could start with the train loader and then move on to the validation loader. So first, let's just set the batch size. Size, of course, batch size. We'll move on to this in a bit, but we're going to be using something called batch normalization in our network. This doesn't work when you have one example in the data set, which can happen, or one example in the batch, because batch normalization computes population statistics or batch level statistics, and it won't work with one example. So that's the whole point of using the drop last equals true flag here. Okay, so you should get something out like this. So it's basically stacked all of the examples into millibatches of shape 16, which is our batch size, and five columns, which correspond to our features. And the shape of the target is 16 times 3, because you've got the unit vector, which is of length 3, corresponding to the number of species. Okay, is everyone okay with that? Yeah.
If you guys see that in the train loader, we have shuffled the data, shuffle is equal to true, but in the valid loader, we have not shuffled the data. That is because shuffling the data doesn't make any sense in the valid loader, but it does make a lot of sense in the train loader because it will help you generalize your model. You can, absolutely, but it won't make any difference. Precisely.
Everyone okay? Okay, the next step is to create a neural network, and we've got like 5 minutes before the break. I'll just introduce what we're going to do here. There's a lot of text, which you feel free to read at your leisure, but the whole point is to use this nn.module class. This basically embeds all of the things that are useful for making a neural network. A neural network's architecture, so linear layers and dropout layers, normalization, etc. So it also has some really useful methods like parameters, which allows you to just, which you'll see later on, but that parameters extracts all of the weights from the network, and you can actually have a look at them and feed those into the optimizer. We have another magic method called call. This allows you to, this basically just calls the forward pass of the model. I just explained torch.nn.linear, which is a subclass of module. So layers, I briefly described this in the lecture at the start, but we're just doing this matrix operation where W times X plus a vector of biases. We also need to apply activations at each stage, as I introduced. You can think of them as layers, but they don't really have any tunable parameters. And the way we're going to do this is we're going to define the architecture within the init function, and all of the subcomponents of our model will go here. So there's a bit of content here about how PyTorch works under the hood. I'm not going to go into it in too much depth, but the forward pass basically builds this computational graph, and then when you want to compute the gradients, this computational graph is used to just backpropagate through those layers. Okay, so we've got like 5 minutes. I can just start with creating a neural network, or just demonstrate how to do it badly, probably. I think I'll just illustrate how this is done in a really bad way, so that we can show how you might want to do it in a good way. But maybe I'll wait until. Oh, I might as well do it now. But commonly, what you see in research code is something like this, where you get linear layers which are defined basically hard code the layers into the init like this.
So you're basically just defining the structure of your neural net, all the layers that you are going to use, all the activations, and then in the forward function we are just going to define how data is going to flow through each of these layers.
So this is what you kind of commonly see, where you assign these the structure of the architecture to these class variables, so that whenever you want to modify the architecture, you have to keep going back and forwards, and yeah, it's not very sustainable code. So there's a better way of doing this, which I think maybe I'll wait until after the